Hello dear students, welcome to Experimental Techniques and Material Characterization lecture number 31st. I'm Dr. Parvez Ahmed. In this lecture, we will continue our discussions on the Raman Spectroscopy. This is part number 2nd. So here we will discuss about the Raman effect and Raman shaft. So let's proceed towards today's lectures on the Raman effect and Raman shaft. So first we will start our discussions from Raman effect. So we having questions in mind that what is a Raman effect. So let first clarify the concept of Raman effect. That what is the Raman effect? So you can also see here. Schematically, you can also see the process of the Raman effect. But how we define the Raman effect? The Raman effect is based on the scattering of light, which normally from a laser source, and that scattering, it includes both elastic scattering and inelastic scattering. The elastic scattering we call Rayleigh scattering, and it is at the same wavelength as the incident light. And inelastic scatterings we call Raman scattering, and it is a different wavelength due to molecular vibrations. We have two type of scattering. One is elastic scattering that we call Rayleigh scattering, and the other is called inelastic scattering that is called Raman scattering. The Raman scattering is inelastic. It has a bit different wavelength, and that is because of due to molecular vibrations. And you should remember that Raman scattering is about a million times less intense than Rayleigh scattering. Therefore, to obtain Raman spectra, it is necessary to prevent Rayleigh scattering from overpowering the weaker Raman scattering. So here again you can more clarify your concept, and this is if you can clearly observe here. So this is a molecule. This is the molecule, and here we shines the laser light on the molecule. So after that we have scattering, so you can easily observe the scattering. We have a scattering that is the the inelastic scattering that we call Stoke-Raman scattering, and here we say the scattering wavelength is a bit greater than the wavelength of the shining laser. And along with that we have Rayleigh scattering, which is almost the same wavelength as that with the shining lasers wavelength, and anti Stoke-Raman wavelength. So here you can see again the scatterings wavelength is a bit shorter than that of the laser wavelength. So Raman spectra are measured by exciting a sample using a higher intensity laser beam, with resulting scattered light being passed through the spectrometers. Now let's come towards the Raman shaft. Normally most of the people they are confused with the Raman shaft. So what is the Raman shaft? So let me first clarify the concept of Raman shaft. The Raman shaft is the energy difference between the incident light and the scattered light. So from here on you can clarify your concept. So here you can see we have different energy levels. These energy levels they are being clarified here. So how you can clarify your concept of the Raman shaft? So the Raman shaft, just like I mentioned, is the energy difference between the incident light, the light that we put on the sample, and the scatter light, the light after shining, after striking the sample, that light then scatter. So to find out the energy difference between the incident and scatter light, that we call in Raman spectroscopy as the Raman shaft. So in the resulting spectrum, the virtual axis, that we take along the y-axis of the scatter light, that is taken as the intensity. The virtual axis here, you don't see it here, but normally we put it here along the y-axis, and we note it as intensity, and along intensity we put our battery unit. So that is taken as the intensity, while along the x-axis, that is the horizontal axis, along with that we take the wave number of the Raman shape, that is an per centimeters. So let me clarify it more. The Raman shaft is associated with two different energy band. So here you can see the Raman shaft is associated with the two different energy band. So the shaft at a wavelength higher than that of the incident light is termed as Stokes scattering. So here you can see this is the sketch. This is the spectrum for the Stokes scattering, and here you can see it. And be remember the shape at a wavelength lower than that of the incident light is termed as anti-Stokes scattering. So as an example, the Raman spectrum of sulfur measured with excitations wavelength of 532 nanometer, that also we call green laser, is shown here. This is the sulfur Raman spectrum. This is for the sulfur Raman spectrum, and that's been taken with the laser excitations of 532 nanometers. So Stokes scattering is observed in the lower wavelength, it mean the longer wavelength regions, and anti-Stokes scattering and the higher wave number, that is shorter wavelength. Shorter wavelength is being shown here. So you can observe the Stokes scattering and it's anti-Stokes scattering. So typically, higher intensity Stokes scattering peak are used for the analysis. These are the high intensity peak. They are being utilized for the Raman analysis, but we also do not ignore the anti-Stokes peak because it can also be used for the analysis. So both of these peak, that be used in Raman analysis, but the importance, is given to the Stokes one. The Stokes scattering. So let me clarify a bit more about the Raman shape. So here you can see in the figure. By having a clear look at the figure, you can easily clarify your concept that the wavelength of the Raman scattered light will depend on the wavelength of the excitation light. So this makes the Raman scatter wavelength an empirical number for comparison between the spectra measured using different lasers. So the Raman scattering positions is therefore converted to a Raman shift away from excitations wavelength. So here this is the relation for Raman wave number. You can clearly observe that how the intensity, the wavelength of the incidence laser beam and that of the scatter laser beam, how that's been linked with the final wave number. So be remember in these relations, the first term, which you can see it here, that we have put with the lambda naught, that is the wavelength of the excitation laser. We take that in nanometers, which I mentioned in the previous slide is about 32 nanometers, and lambda with the subscript 1 is the wavelength of the Raman scatter in nanometer. So this is the relations for the wave number, or we can say the Raman scatter positions. There is also another concept which we call vibrational modes. So Raman spectroscopy measures the energy gap between the vibration level of the molecules. So the ladder of vibration level shown here in the in this figure, it's basically for a single vibrational modes of the molecule. So for polyatomic molecules will contains many vibration mode, each with their own ladder of vibration. That we see this is for a single molecules. But if we have many molecules or we have polyatomic molecule, so then what we will do for the polyatomic molecule? So for non-linear molecule with n atoms, the number of vibration mode is given by the relations 3n minus 6. So what is mean by 3n? The 3n is the total degree of freedom of the molecules, and the translation 3 degree of freedom, and the rotational and the 3 degree rotationals are then subtracted, which leave 3n minus 6 vibrational mode. So for linear molecules, there is one less rotational degree of freedom, and the number of vibrations mode is therefore 3n minus 5. But along with that, you should also remember that not all the vibrations mode can be detected using Raman spectroscopy. So for a vibrational mode to be measured, it must be Raman active, which occur when the molecular polarizability changes during the vibrations. So that's all we have for this lecture. Thanks for watching. But stay tuned with the next lectures on Raman spectroscopy. In that lectures, we will differentiate between the Raman spectroscopy and infrared spectroscopy. So stay tuned with the next lecture. Till then, bye bye.